Okay, so I'm recording this before I'm teaching Thursday today. So if I say some things redundantly, it's just because I have not gone over units 1 and 2 yet. Okay, so the first problem that we're going to go over from unit 3 is problem 38, which is finding all real and complex roots. So if you guys remember, the real roots were just, well, roots, first of all, let's remember what that means. Roots is a synonym for x-intercepts. So you can find the real roots just by graphing the equation. So that's pretty easy to do both on a graphing calculator, if this was not an EOC, or on Desmos for the situation with an EOC. The complex roots are the ones with the I in them, which is why you're seeing answers in here with I. So if you recall, this was that one unit where we used our cheat sheets, where you guys kind of had a hard time because the unit felt, it really did flow together well, but it felt weird. Like we learned a lot of different stuff in the unit. So the process for these was first to graph it on your calculator to find the x-intercepts, like the real ones. So the real roots, to find the x-intercepts in the calculator. And then after you found the real roots in the calculator, then you did synthetic division with each of them. So if there were 3 real roots, you did synthetic division 3 times. If there was 2, you did it twice. If there was only 1, you did it once. You did it however many times you had x-intercepts. And then when you were done with that, you were left with a quadratic, and you did the quadratic formula. And when you did the quadratic formula, you were always going to get an answer with an I in it. The answers always had I, because if they had been real, they would have shown up on the graph. So the resulting answers after this were imaginary. So we would look at the beginning of the problem and be like, oh, it has an x to the 4th. That means there's 4 answers. So if you guys vaguely remember that, hopefully. So what we're looking at here is we want to be able to find 4 answers. You can see that all of these problems do have 4 answers. They have 2 imaginary answers and then 2 real answers. And the nice thing about this problem is that for this problem, all of the real answers are different. So that means we actually don't have to do this process. We're just going to be able to graph it, find the real x-intercepts, and call it good because the real x-intercepts are all unique. So you could do that on a regular graphing calculator. You could do it on Desmos. As long as you can use a calculator on this problem, you don't have to really know how to do it because it has the word roots in there. And we know that means x-intercepts. So let's go ahead and graph this on Desmos. So we are going to Desmos. We're going to graph this. We've got 2x to the 4th minus 9x to the 2nd minus 81. And we're just going to look to see where it crosses the x-axis, which is at -3 and +3. And so we can see that the correct answer there is D. The next problem that I wanted to go over was 40. And so 40 has different problems that they want you to factor. So to check anything like this, and pretty sure we're going to talk about this today when we go over units 1 and 2. But anytime you want to talk about whether or not something is equivalent, you can just graph both of them and make sure that they line up. So for 40, we're just going to graph the first one, 4k squared minus 49, and then we're going to graph the factors and we're going to make sure they line up, and then we'll know if that factorization is correct or not. So Desmos doesn't like us to use other variables, so we're going to use x every time, So 4k squared minus 49, I'm just using x's. And then the factors 2x plus 7, 2x minus 7. So yes, those were the same, okay? Then we have a cubed minus 8b cubed. So I'm going to do x cubed minus 8y cubed. Desmos doesn't like this because it's got two variables and it's not an equation. So I'm just going to put equals 0, turn that into an equation. And then I'm going to do the same thing for the factors. So I've got x minus 2y. And then I've got x squared plus 2xy plus 4y squared equals 0. Okay. And so anytime I don't want to have a bunch of different things on the screen, I can just turn them off on Desmos by clicking these. So those two were the same, and I'll go ahead and turn them off. These two are the same, so I'll go ahead and turn those off. So those were both factored correctly. The next one is all in terms of m, so I'm going to go ahead and do that all in terms of x. So x to the third plus 3x squared minus 4x plus 12 equals, gotta make sure I keep the x's in there. X minus 2 squared, and then x plus 3. So here you can see that these do not line up. So I've got the green, I've got the black, those are not the same. So it's looking like this is probably the answer where it's the factorization is wrong. I can do the last one just to be sure. I'm pretty sure this is it, but I can do the last one just in case. X to the third plus 5x squared plus 6x plus x squared plus 5x plus 6. And we got x plus 1, x plus 2, x plus 3. So here the red and the blue are, let me turn that one on. Red and the blue are actually the same. And so we can see that it was the third answer where the factorization and the function itself were not the same. So let me go back and circle my answer of this one right here. They were not the same. So that strategy works for a lot of problems, just graphing to see if they're the same. Okay, let's move on to another type of problem. 44. So we did a lot of these in the unit, if you guys remember when we were doing long division. We did something called the Remainder Theorem, and I think you guys kind of got confused by it, and then you kind of understood it, maybe liked it a little bit, kind of saw the purpose of it. So if you guys remember when we were doing long division, if we were doing this problem longhand, the way that they want us to do it, we would have said 4x to the third plus 0x squared plus 5x plus 10. We would divide that by 2x plus 3. And then we'd get all this stuff. We go down, 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 down. And we'd get down here and we'd have some sort of number. And then we'd get something up here like something x squared, blah, 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 plus some sort of number divided by 2x plus 3. We'd get something like this. This is what our answer would look like. And then we learned after we did this, we learned about the remainder theorem. And the remainder theorem said, well, if you're gonna take this and divide it by 2x plus 3, go ahead and just take the thing that you're dividing by and set it equal to 0. Okay, so we're going to go, all right, 2x plus 3 equals 0, and then solve for x. Okay, so minus the 3 minus the 3, 2x equals negative 3, divide by 2, divide by 2. So x equals negative 3 halves. And then the remainder theorem told us that if we took the top and thought of it as a function, we could take the x and evaluate that function at this x value. So we would say 4 times negative 3 halves to the third plus 5 times negative 3 halves plus 10. And you can plug this into Desmos, or you can plug this into your graphing calculator. For this problem, it doesn't really matter. I'm a little bit quicker on my graphing calculator with this sort of thing. You guys know my buttons are broken in on the calculator. So I'm going to go ahead and type this real quick on here. And then this is the remainder. So that if you were to evaluate it, this ends up being the remainder. So this is negative 11, which is the exact same number that I would have gotten down here, which is the exact same number that I would have gotten up there. This is the remainder theorem, if you guys remember that. So the nice trick about this is that if you look at the problem and all of your remainders are different, then you can look and say, oh, my answer's 2. Okay, now of course you can do the same thing that we did on, what problem was it that we just did? We just did problem 40. So you can do the same thing we did on 40, where you can type the original problem, and then you can type these and just see which ones, where the graph matches up. In fact, let's do that. Let's just make sure that these two graphs match up. So I'm going to go ahead and go to Desmos right now, because we know that Desmos is really good for just all these problems. We love that the EOC lets us use Desmos. Feel bad for the kids who took this class before they were allowed to use Desmos. So 4x to the third plus 5x plus 10. And then on the bottom, they've got 2x plus 3. And we're just going to make sure that C looks the same. Because when you divide these, you don't get a different answer. You get something that is equivalent to that, and the answer just looks different, but it's equivalent. So 11 over 2x plus 3. There we go. It's the exact same thing. Green, purple, green, purple, or blue. Would you guys call that blue? No, that's purple. All right, so those are the same answers, and that was two different ways of getting it. One way I used the remainder theorem. The other way, I used graphing. All right, let's use the remainder theorem to do problem 45. We did one like this in class, actually. I put it on our worksheet. So it says we're going to do f of x, and we're going to divide it by x plus 2, and the only information we have is the graph on the right. So we've got f of x divided by x plus 2. So the only thing we can do is we can take the x plus 2. I'm going to take it off to the side. I'm going to say, all right, x plus 2, set it equal to 0. Okay, so minus 2 over, I'm solving for x equals negative 2. So what I'm going to do now is I'm going to take that 2, that negative 2, and I'm going to plug it into the function that's on the top. I'm going to plug it in. So I've got f of negative 2, and I'm going to see what that equals, because that's going to equal that remainder, because this is f of x divided by x plus 2. And if you were to do all the work, then you get the remainder down here, and the remainder is what they wanted to find. Okay, so f of negative 2, plug in negative 2, f of negative 2 is negative 6. That's the answer right there. F of negative 2 is negative 6. Okay. Let's see if we can do one last problem before the bell rings. All right. 57 says that given that x plus 2 and x plus 1 are factors of this polynomial, what's the third factor? Okay, so that means we're going to graph this. This is what we're going to start off graphing, and we're going to compare it. So we know that this polynomial is x plus 2 times x minus 1. And then it's got another set of parentheses. And that last set of parentheses is either this, 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 or this.